Hello guys, welcome back to my channel, and in this video I would like to basically evaluate and analyze some integrals. So let's get started. This video is kind of a unique one, so you'll see why. So let's get started. So the first integral that we're going to work with, let's call it I1, is defined as integral from 0 to infinity of natural log of x divided by 1 plus x squared dx. So looking at the denominator that we have here, 1 plus x squared, this looks like one of those standard substitution cases of basically differentiation and also trigonometric substitution. So this denominator is actually screaming to us to use this substitution. Let x equal to tan theta such that dx is nothing but secant squared theta d theta. So I1 just becomes integral from 0 to pi over 2 now because we have a tangent. Natural log of tan theta divided by 1 plus tan squared theta, and we have a secant squared theta d theta in place of the dx. Now basic square identities of trigonometric functions, we have natural log of tan theta on top divided by 1 plus tan squared theta is secant squared theta, and we have a secant squared theta here d theta. Cancel both of them out, and that was the entire usefulness in this substitution. So we integral from 0 to pi over 2 of natural log of tan theta d theta, but tan theta can be expressed as a ratio of sine theta and cosine theta like this. So I can write this as integral from 0 to pi over 2 of natural log of sine theta divided by cosine theta d theta. And there is one nice property of logs. So if you have log of any base of a over b, you can split this up as log to that base of a minus log to that base of b. So we can write this as a difference, integral from 0 to pi over 2 of natural log of sine theta d theta minus integral from 0 to pi over 2 of natural log of cosine theta d theta. And we can just use symmetry for the second integral. We have natural log of sine theta d theta as it is, minus integral from 0 to pi over 2 of natural log of cosine of upper limit plus lower limit. So pi over 2 plus 0 is pi over 2 minus the original variable theta, rest unchanged. And you can simplify this to integral from 0 to pi over 2 of natural log of sine theta d theta minus integral from 0 to pi over 2 of natural log of cosine of pi over 2 minus theta using basically complementary angles identities is sine theta d theta. And look at that, same terms subtracted from each other, so all of this will give us 0. So I1 is equal to 0. So all of this is 0, all this trouble for nothing. Now let's do another integral, let's call it I, defined as integral from 0 to infinity again of natural log of 1 plus x squared divided by 1 plus x squared dx. So now again notice the denominator screaming at us to use the standard substitution, x equals tan theta such that dx is equal to secant squared theta d theta, just like our last integral. So I is equal to integral from 0 to pi over 2 now of natural log of 1 plus tan squared theta divided by 1 plus tan squared theta and secant squared theta d theta over here. We can write this as integral from 0 to pi over 2 of 1 plus tan squared theta is secant squared theta in the numerator and denominator, along with the secant squared theta d theta. Secant squares will cancel off like this. We are left with integral from 0 to pi over 2 of natural log of secant squared theta d theta. Now there's this nice property of logs. Say if you have log of a to the power b, this can be written as b times log of a. So we can bring the power down. We have 2 times integral from 0 to pi over 2 of natural log of secant theta d theta. But secant is just the inverse of the reciprocal of the cosine. So we can suck out a negative and then flip the argument of the natural log on itself. So 1 over cosine when flipped becomes cosine. So we just have natural log of cosine theta d theta. And again, if you want to use the symmetry, we have minus 2 times integral from 0 to pi over 2 of natural log of cosine of pi over 2 minus theta d theta. This will become minus 2 times integral from 0 to pi over 2 of natural log of sine theta d theta, and I had actually made a video on this. So this will just turn out, if you can watch it if you want, minus 2, and this just turned out to be minus pi over 2 times the natural log of 2. So the negatives cancel, the 2's cancel, we end up with pi times natural log of 2, which indeed is the correct value of this integral. So now, unlike my previous videos, where we just ended the video with the direct solution, I'm going to explore other methods of solving this integral. So let's do that on a fresh page. So again, this is the integral that we have to calculate. Why not use Feynman integration technique? You may also know it as Leibniz rule, and I've commonly called it Leibniz rule because it's shorter to say. For that, you need to parameterize this thing. So first parameterization is going to be inside the natural log argument. So integral from 0 to infinity of natural log of 1 plus tx squared, like this, divided by 1 plus x squared dx. And when I take the partial derivative with respect to t, I have I prime of t, which is going to be integral from 0 to infinity of, well, use the chain rule now. We have 1 plus x squared as it is, and then even this argument goes in the denominator, 1 plus tx squared, and in the numerator we just end up with an x squared, right? The derivative of 1 plus tx squared with respect to t's x squared dx. And looking at the product of factors in the denominator, this actually calls for partial fraction decomposition. And for this video, I'm going to skip all the steps of partial fraction decomposition. You may, if you don't agree with my method, my values of after partial fraction decomposition, you're really welcome to try it on your own. So what I obtained is I prime of t is equal to 1 over t minus 1, which is a constant with respect to x, integral from 0 to infinity of dx over 1 plus x squared plus 1 over t minus 1 times integral from 0 to infinity of dx over 1 plus tx squared. Well, calculating this integral is pretty easy. We have 1 over t minus 1 times the inverse tangent of x evaluated from 0 to infinity, plus we can take a t out over here, factorize a t times t minus 1. We have integral from 0 to infinity of dx over x squared plus 1 over t, which I choose to write as 1 over square root of t, the whole thing squared, which essentially is 1 over t. I've just written it with a square root and a square of that. And calculating this is easy. We have, for infinity we have pi over 2, and for 0 we have 0. So this is just pi over 2 times 1 over t minus 1 plus, well, again, this is of a standard type. This will be square root of t over t times t minus 1 times inverse tangent of x times square root of t evaluated from 0 to infinity. Again, for the infinity case, infinity times a constant is still going to tend to infinity. We have pi over 2 again here. and for 0 we have 0. So pi over 2 times 1 over t minus 1 originally, plus I can reduce 1 square root of t. I have 1 over square root of t times t minus 1, and this just evaluates to pi over 2 as I said. So pi over 2. That's basically your I prime of t value. Now we have to reintegrate this with respect to t, choosing proper upper and lower bounds such that we arrive at I again. So before starting with the integration process, let's see how this I of t relates to I. So notice that I of t when t equals 1 is just our original integral I. And I of t when t equals 0 is equal to 0 because we have natural log of 1 which is 0, and 0 over 1 plus x squared for any x is going to be 0. So why don't we integrate from 0 to 1 such that, because if we do that, if we integrate I prime of t from 0 to 1 with respect to t by fundamental theorem of calculus, we'll end up with I of t evaluated from 0 to 1, but I of t when t equals 1 minus I of t when t equals 0. These are basically upper and lower bounds evaluation. I of t when t equals 1 is I just said that, and I of t when t equals 0 is 0. So I minus 0 is I. So I, our original integral that we intend to find, is integral from 0 to 1 of I prime of t dt, but we have an expression for I prime of t. So let's integrate that instead. We have integral from 0 to 1 of pi over 2 times 1 over t minus 1 dt plus integral from 0 to 1 of pi over 2 times 1 over square root t times t minus 1 dt. So this first integral is easy to calculate. It's just pi over 2 outside times natural log of absolute value actually of t minus 1 evaluated from 0 to 1 and plus pi over 2 integral from 0 to 1 of dt over square root t times t minus 1. Okay, so I'm not going to evaluate this because if we evaluate this at t equals 1, we have natural log of 0 which basically diverges to negative infinity, and when we plug in t equals 0 we have natural log of negative 1, and although it's in an absolute value, but yeah, you can take it as a 0 just because we have an absolute value. So I'm just going to leave this as it is for now. So I'm just going to write this, keep writing this is pi over 2 times natural log of t minus 1 evaluated from 0 to 1. And we could use a little u substitution, or in this case y substitution. So I'm going to let y equals square root of t such that y squared equals t, so dt is 2y dy. Upper and lower bounds remarkably remain unchanged. So pi over 2 times integral from 0 to 1 of dt is 2y dy over y times y squared minus 1. The y's will cancel out nicely. We have pi over 2 times natural log of t minus 1 evaluated from 0 to 1 plus 2's will cancel. We have pi times integral from 0 to 1 of dy over y squared minus 1. So we have pi over 2 times natural log of t minus 1 evaluated from 0 to 1 plus, and there's an integration formula for this. You can use partial fraction decomposition. You may use trig substitution also. But I'm just going to directly write the answer. Pi over 2 times natural log of y minus 1 divided by y plus 1 evaluated from 0 to 1. And this we can just write as pi over 2 times natural log of t minus 1 evaluated from 0 to 1. I'm sorry, it turns out I made a slight error with this. There was a negative all along. So Just making those changes quickly. I mean, yeah, if in case you are like an avid viewer, you might have noticed, plus looks kind of fishy. My notes just got too scrambled this time. So negative pi over 2 times natural log of y minus 1 evaluated from 0 to 1 minus minus plus pi over 2 times natural log of y plus 1 evaluated from 0 to 1. Notice that these two cancel out, doesn't matter what variable we have. It's property of definite integration for even these evaluating these functions. We end up with pi over 2 times natural log of y plus 1 evaluated from 0 to 1. And we evaluate that, we get pi over 2 times natural log of 2 minus pi over 2 times natural log of 1, which is 0. We end up with pi over 2 times natural log of 2. But hey, wait, that's I, right? That's what this thing should be equal to. But there is something wrong, because if you remember the original trigonometric substitution process, we obtained I is equal to pi times natural log of 2. Why is there a disparity? How did we just get the constant 2 over here, in the denominator? How does that even make sense? Notice what went wrong in this method is the fact that we separated this integral over here, because this is going to diverge. Natural log of 0 tending, goes to negative infinity, just keeps on decaying, approaching a really, really small number. All of this is going to diverge. So, and what we did over here with cancelling similar terms was basically doing sort of an infinity minus infinity situation, and this, is loosely defined. Infinity can be anything. You can multiply 2 over here and still call this an infinity. So, we could have multiplied this expression, rather, this part by 2, and we have to do that for this too. And both of them would still have cancelled, because even this going to a negative infinity, 2 times negative infinity is still going to be negative infinity. So, you know both of them would still have cancelled under the assumption that the limit that y goes to 1, natural log of y minus 1 will go to infinity. So multiplying, dividing by any number doesn't change that. So we could have divided by any constant, call it pi, a, 8, any constant, and we would have come up with a similar answer, but modulated by whatever constant we divided by. We could have gotten rid of this 2 that we don't want actually by multiplying by a 2, or multiplying even by an 8 and getting a different answer. So that's what is wrong. So never, it's mathematically unhealthy to separate divergent integrals like this. So divergent integrals separately will just be infinity, and infinity minus anything finite. This turned out to be finite, right? I mean, half of it turned out to be finite though, but so infinity minus something finite like k, infinity minus k will still be infinity, right? This is not mathematically accurate notation, but I'm sure you get the idea with this. That's why this method entirely is, I mean, everything until here was right, but then afterwards, when we integrated both sides and we took this as a separate integral, the divergent integral, that's when everything went wrong. Now let's look at another way of doing this, again using Feynman integration technique. But with a slightly unpopular substitution, unpopular parameterization. So if I say I of t equal to integral from 0 to infinity of natural log of 1 plus x squared, the parameterization is not inside the natural log, but instead with this e raised to minus t times 1 plus x squared divided by 1 plus x squared, and the motivation for this parameterization was to get rid of the denominator on performing the partial derivative. So I prime of t is going to be negative because of negative t, integral from 0 to infinity of natural log of 1 plus x squared divided by 1 plus x squared multiplied by 1 plus x squared now, because that's chain rule, e to the minus t times 1 plus x squared dx. Notice these two things cancel out nicely. This minus integral from 0 to infinity of natural log of 1 plus x squared times e raised to minus t, and in the power we have plus x squared t, which we can write as e multiplying e to the minus x squared t, with the entire thing dx. E to the minus t does not depend on t, we can take it up, does not depend on x, sorry, we can take it out. E raised to minus t outside, integral from 0 to infinity of natural log of 1 plus x squared times e to the minus x squared t dx. Now let's perform this quick substitution. Let w equal x squared t such that x is nothing but square root of w over t. So dx is 1 over 2 times square root t times square root w. Upper and lower bounds remarkably remain unchanged. We have e raised to minus t with a negative. Integral from 0 to infinity of natural log of x squared is w over t. 1 plus w over t e to the minus w. Forgot a dw here. So this is going to be dw. Dx is dw over 2 square root t times square root w. Take the 2 and the square root t outside with negative e raised to negative t divided by 2 times square root t. Integral from 0 to infinity of natural log of 1 plus w over t. We can write this as w to the negative half power e to the minus w dw. And at this point, if you insist that we use the Taylor series for the natural log, we can do that because this is of a convenient form. So we can say e raised to minus t with a negative over 2 times square root t, integral from 0 to infinity of sum from k equals 1 to infinity of minus 1 to the k plus 1 over k times w over k over t to the k times w to the negative half e to the minus w dw. Assuming uniform convergence now, assuming uniform and absolute convergence, we can then propose to interchange the sum and the integral, and we take all the terms that basically don't depend on w outside. So we have basically sum from k equals 1 to infinity with a negative minus 1 to the k plus 1 divided by k times 2 e raised to minus t in the numerator, and this t to the k and this t to the half will make t to the k plus half in the denominator, and we basically have integral from 0 to infinity of e to the minus w to the k minus half, combining these powers dw. But notice what this is. This looks like a gamma function, right? Gamma of what? Well, this exponent of w plus 1. So k minus half plus 1 is k plus half. So all this becomes in a sum from k equals 1 to infinity of minus 1 to the k plus 1 times e to the minus t divided by 2k times t to the k plus half. This is gamma of k plus half. That essentially is your I prime of t. But in this case, upper and lower bounds are also 0 to infinity, because notice that in this parameterization, say if you let t approach infinity, this term is going to decay to 0, so we'll have 0 times something divided by something, which is going to be 0. And when t equals 0, that's going to equal I. our original integral, because e to the 0 is 1. So I is basically negative integral from 0 to infinity of I prime of t dt, because that will give us minus I when t approaches infinity plus I when t equals 0, and this is 0 I showed you, and this is I, so this becomes I, that's why. And we have an expression for I prime of t, so I is negative times this negative will cancel out. We have basically sum from k equals 1 to infinity. Again, we assumed uniform convergence, we took the sum outside, integral inside, minus 1 to the k plus 1 divided by 2k, and then gamma of k plus half. Take all the t terms inside, so integral from 0 to infinity of e to the minus t, and this will be t to the minus k minus half power dt. This is again a gamma of minus k minus half plus 1, which is gamma of minus k plus half. So we have sum from k equals 1 to infinity of minus 1 to the k plus 1 divided by 2k, gamma of k plus half, and we have gamma of negative k plus half. And at this point you may say that this is a dead end, but notice that if you let this equal z, this is just 1 minus z. So we essentially have something of the form gamma of z times gamma of 1 minus z, which by Euler's reflection formula is pi over sine of pi z. So when we do that, we have sum from k equals 1 to infinity of minus 1 to the k plus 1 over 2k pi over sine of pi times z was k plus half. So we have pi k plus pi over 2, which if you want to write in terms of like this, say inside the argument pi over 2 minus pi k inside a sine. You can use complementary angle, you will have a cosine of negative pi k, which cosine is even, so we'll have cosine of pi k. This will become pi over 2 outside, sum from k equals 1 to infinity of minus 1 to the k plus 1 over k times cosine of pi k. But notice that k is an integer, right? It's k is going to be 1, 2, 3 till infinity. So k belongs to the set of all integers, positive integers rather. So what do we have when we have pi times a positive integer inside a cosine? Well, notice that for integral multiples of pi, see this is when we have 0 pi, 2 pi, 4 pi, even multiples of pi this side, this angle subtending 0 degrees. And then subtending 180 degrees, we have odd multiples of pi, such as 1 pi, 3 pi, 5 pi. All these angles are equivalent. So cosine at even multiples is going to be 1, cosine of 0 is 1. Cosine at odd multiples is going to be minus 1. So for odd multiples, we can say minus 1 to the k, where k is a multiple of pi. So if we have an odd multiple, we have minus 1 to an odd power, which is minus 1, matches this value, and minus 1 to an even power for an even multiple will give us 1, matches this value. So cosine of pi times an integer is minus 1 to that whatever integer that is. So pi over 2 times sum from k equals 1 to infinity of minus 1 to the k plus 1 over k times minus 1 to the k. Minus 1 to the k's will cancel, minus 1 to the 1 will remain, giving us minus pi over 2 times sum from k equals 1 to infinity of just 1 over k. And notice this is the harmonic series. So we just have limit as k goes to infinity of minus pi over 2 times the kth harmonic number. And this diverges, right? The summing inverse terms with each other, basically harmonic series till infinite terms, will diverge, right? It's a famous series. I hope you know this. So I, with this method, is saying I diverges. So what went wrong here? Because we know that the real value of I is pi times natural log of 2. So what went wrong here really? Well, you know, since this method is really weird, involving gamma functions, so you might want to check on the definitions of gamma functions. But what my theory says, what went wrong likely in the most likely scenario is this assumption. Assuming uniform convergence is a very loose assumption in case of integrals from 0 to infinity involving gamma type function, because this assumption is most likely to break with integrals of this integrands of this form, basically, involving gamma like integrands. So that's where there is a likely chance of this assumption to break. And it's not this assumption is this place is not the first where we've actually used this assumption. We've used the assumption again when we were reintegrating, when we took the sum outside the integral over here, when we basically took the sum outside the integral. That's where we again use this assumption. So there are two dangerous places where stuff could go wrong and essentially blow up to infinity, and it looks like that's exactly what happened. This assumption, it seems, is wrong in, I don't think only one place, but both of the places, because again we had a gamma type or gamma like integrand over here. So these things are pretty sensitive. We need to deal with them with caution. So if you end up with some weird answer like infinity, you may want to try using different methods, and again cross check your answer with different methods, and try not to deal with separate divergent integrals like approach number 2, the approach before this. So I hope you got a little insight onto which techniques work, when they work, and when they don't work. So that's it for this video. So guys, please like, share and subscribe to my channel. Recommend me to your friends. I'm upgrading my content almost once in like 2 to 3 weeks. So you might notice the increasing level of my videos. But anyways, I need to grow. I need more followers. That's how you encourage me to make more videos. So please spread this, share videos. And you can follow me on Instagram, gamma_digamma. And in the meantime, stay home, stay safe. Have a great day.